Okay, so we're recording. So here's where we were last time. We were talking about the multivariable chain rule. Keep in mind the big idea is that when you compose two functions, if you have a sequence of functions, first you do f, and then after that, whatever comes out, you then do g. All together, that's called the composition. Right? We have this uses standard notation for it, like this. Well, let's see. Here's a better one, like this. Right? And what we argued is because for each one of these, for example, what turns x prime into y prime is, well, multiplication by a factor. The factor is the matrix called df. Right? And then, okay, well, what turns y prime into z prime? Well, multiplication by another factor. This time it's called the derivative matrix of G, so dg. And so altogether, that two-step process is what turns x prime into z prime. In other words, altogether, the product of those two factors is going to be the derivative matrix for that composition. And so all of this comes down to this formula right here. Which I think, again, is very conveniently and pithily summarized by this statement right here, that differentiation turns compositions into products. Rolls off the tongue really nicely, right? So, in particular, here's the composition, and here is it having been turned into a product of individual derivatives. So the derivative of the composition is the product of the individual derivatives. Okay. All right, so that's where we left off last time. I will point out here's a couple of little notes that have to get made. The example that I've drawn a picture of here is where we have a function that goes from 2 dimensions to 2 dimensions, and then composed with the next function that goes from 2 dimensions to 2 dimensions. So how does all of this change if the dimensions aren't all the same? Right? So this is 2 to 2 to 2. Is it a different rule if the dimensions are different? And no, not at all. Not even a little bit. Right? In fact, here I can make this a 3-dimensional intermediate space here by, okay, now I'll put a y3 there. Okay, now this is a 3-dimensional intermediate space. And notice it's still df. That turns input velocity to output velocity. It's still dg that turns this input velocity to this output. Everything, all the algebra is exactly the same. Right? So don't get too tied up in the picture and the dimensions that I happen to draw here. That was just kind of arbitrary and for sort of convenience. This applies for any dimensions. Next little observation I want to make is that we've observed that df is what turns x prime into y prime, and here it is, df. Right, yeah, but when I say df, I mean as applied at a particular location. Where specifically are we when we claim that we're moving with this input velocity x prime, for which we want to know the resulting output velocity y prime? Well, we're at this point A, that's where we are. So that's where the df matrix has to be evaluated, right? So that's why this is evaluated at the point A. So sure, seems reasonable. But now let's look, though, at the dg matrix. Now the dg matrix turns y prime into z prime. And same question. Where are we evaluating this dg matrix? Where am I when I'm moving in the domain of G, when I'm moving with velocity y prime? Where am I? Well, I'm not at A. Right? A lot of students misunderstand and think that, well, you're supposed to plug in the input point, and the input point's A. That's not where you are when you're in this space moving with that velocity. At that moment, you're at f of A. And that's why this dg matrix is evaluated at f of A, not at A. Commonly misunderstood and confused, and I'm going to say a few more words about how to avoid. There's actually kind of a confusion of variables to be worried about in situations like this, and there's a really nice way to avoid this problem. We'll talk about that in a few minutes. Okay, so yeah, there's that. One last thing, a little quickie. There's a really tragic notational situation to be aware of. Everything I have on the screen here I think is right, but you may have noticed that F is on the left in the diagram and G is on the right in the diagram, but G is on the left in the composition and on the right. And F is on the right, I should say, in the composition. So what's up with, again, the little switcheroo, right? Why are they in the opposite order? And just like with partial derivatives, remember I was talking about the two different notations for second-order partials? Whether you use subscripts or Leibniz, they get in the wrong order. Morally equivalent problem here. We draw diagrams left to right, but when you write down a composition, right, this composition is literally G of F of the input values X. And so that's why the G has to be written on the left. This tragedy of switching orders, right, comes about unavoidably from the fact that we write functions on the left of what we're plugging into them. And that's pretty deeply embedded in mathematical culture, and I don't know, there actually is a cabal of mathematicians that are trying to change that, and they're not going to succeed. Right? It's too deeply embedded. So this is just an unavoidable source of confusion. And please make sure, don't write F composed G here. That will then have you multiplying your derivative matrices in the wrong order, and it's catastrophically wrong. Right, and again, this isn't a typo. This is a significant, meaningful conceptual point. So that's kind of a big deal on exams and stuff. Okay, so take the time as necessary to kind of straighten it out in your head. Wait, which one is on the left and which one's on the right? Is it the first or the second? And which way does it go? You just got to keep that straight. Okay. All right, let's see an example. So we have a couple of functions here. Here's F, here's G. Notice that the what comes out of F is also what goes in to G. Right? So we are composing two functions here, F first, G second. Notice that that's how I represent the composition. The composition, here it is. G compose F, which means F first, G second. Again, yeah, switcheroo. Watch out for that. Right? Okay. All right. So the question is, assuming these are differentiable functions and various bits of information given. This is all freebie right here. It's part of the statement of the question. And what the question wants us to do is to compute the derivative of the composition, and furthermore to compute this specific partial derivative from the composition. Notice that that is asking for the partial of Z3, the third output variable, with respect to X1, which is the very, very first of the first input variables. Right? Okay. All right. So here we go. The first thing we're going to write down, first of all, let's just focus on the composition derivative. We'll get to the partial derivative in a minute. Chain rule. Just write it down. First step. Now we just have to make sense out of what we're given. Let's see here. Apparently, I need to know the DF matrix at the point 1, 2. Oh, sweet. Lucky break. We were given that, so boom. Nothing to it. Straight up given. Everybody see that? Yeah. As a starter example, I like to start with one where it, it's I don't want to get lost in a sea of differentiation mechanics and stuff like. So nice, convenient example. We can see what goes where. Okay. Now the next thing I'm going to need, so it seems, is DG evaluated at f of 1, 2. I don't actually see that in what I'm given. I'm given DG evaluated at 310. So I'm a little concerned that these might not be the same. Remember, where it's evaluated is actually really important. So what am I going to do about that? Good news. F of 1, 2 is 310. So in fact, the DG matrix we were given conveniently is indeed exactly the DG matrix that we need. And so this is that matrix right there. Everybody on board? Okay. And then matrix multiplication. Y'all are real good at that. So, arithmetic. There you go. Okay. Everybody happy? Okay, let's see here. Next question, going back to the, I just want to get the whole thing on the screen. Come on, there we go. Okay, yeah, okay. So next part of the question was to find the partial of Z3 with respect to X1. Now keep in mind, reminder, Z3 is the third output variable. So we're taking, for the composition, we're taking a partial derivative of the third output variable. And that means that because we're looking in the at the third output variable, we're going to be looking at the third row of our derivative matrix. So what we're looking for is in this row, third row, because third output. Remember, outputs correspond to rows. Okay. All right, let's see here. I also notice I'm taking the partial with respect to x1. x1 is the first input variable. And input variables correspond to columns. So this being the first input variable, I need something in the first column of my derivative matrix. So you can see just by looking at which input and which output, that tells you exactly which element of the composition derivative matrix that you need. And here it is. It's apparently this number right there, which is 3. Everybody okay? Everybody happy? Okay. All right. Good stuff. Let's see here. A couple of special cases I want to talk about. These are actually not news. Everything I'm about to show you on sort of the next 2 pages of notes is stuff we already know. It's just we're going to kind of rediscover it from the point of view of the chain rule. So let's entertain this specific composition right here. Now, of course, the chain rule is how we understand derivatives of compositions. So what's interesting about this composition is that there is one initial input variable. And what happens when you have just the one initial input variable? Well, a couple things happen. For one thing, this first function, since there's only one input, I could think of this one input as being time. Let's just say it's, it's free country, so I'm going to view this as being time. And now, what this function then gives me is position in this space Rn as a function of time. It literally gives me a parametric curve. Right? So it's a really nice special case to be aware of when you have just one initial input variable. That's a parametric curve. And furthermore, because there's just the one input variable, the derivative matrix will have just the one column. Right? And as previously discussed, the derivative matrix for a parametric curve is the velocity vector. So effectively then, this matrix just represents input velocity. And all of these same observations now also apply to the composition. The composition also has one input variable, meaning that the composition is literally a parametric curve in Rm. It's a parametric curve in what you might call F's output space, right? F's target. So a parametric curve, and again with the one variable, again with the one column, that means that this derivative matrix of the composition is, again, just a velocity. This time it's the output velocity. So having just made this observation, the nice punchline is that we're recovering previously known information about this function f and its derivative. What does the derivative of f do? The derivative of f takes, let's see, I'm making some color choices here, an input velocity in Rn, and spits out an output velocity in Rm. So again, as we established a couple sections back, right back in 2.3, that's what the DF matrix does. It turns input velocities into output velocities. So, yeah, anyway, again, this is not news. We already knew this, but it's nice to see how there's connections between things. So that, what we initially saw as just a fundamental interpretation of the derivative matrix can also be viewed, for, if it might be convenient, could be viewed as a special case of the chain rule. Yeah.
I didn't understand why we're not using the notation for partial derivatives there.
Yeah, so like looking at this function right here, right, it is literally a single variable function, right? Now there's multiple output variables, so it's vector valued, but it's literally a single variable function, and so I don't have to hold a bunch of variables constant arbitrarily to get down to something I know how to take a Calc 1 derivative of. I literally already know how to take a Calc 1 derivative of that. So, that's all it is. Is that satisfying?
Yep.
Okay, cool. All right. Okay. Okay, so let's see a really quick example of this. This is, there's nothing new here in this example either. We totally could have done that. I'm actually thinking about moving this to be an example in section 2.3. In this example, we have a function. Let's see here. Here you go. We have a function like that. Formula being given. And I have a parametric curve, effectively, because I have a position and a velocity in my domain. And I want to know, apparently, my output velocity. So I have a function. I know the input velocity. I want the output velocity. Great. Here's our formula. Output velocity is the DF matrix times the input velocity. And, a few details here in terms of, you do have to find the DF matrix. So you got to take the appropriate partials. You have to assemble to make the appropriate DF matrix. You have to evaluate at the point A where you actually are, right? Where F is acting, at least at the moment in question. And all of that being done, it's just arithmetic to follow. Is that cool? Everybody happy with that? Okay, here's another special case. This is a special case of our special case that we just saw. What if, in addition to having only one input variable, what if we also have only one output variable? Well, okay, so having only one input variable, again, means this is just a single column, and furthermore, that's a velocity vector. But now, furthermore, having just the one output means that the output velocity, in addition to having just the one column, also has just the one row. In other words, the output is just a single variable derivative. It's literally the rate of change of what our function is in that context. Further, because there is only one output variable, there is only one row in our derivative matrix. Right, so this is just how our matrix form of the chain rule looks when you just write it down for this special case. Right? And this kind of smacks familiar of two things that we've previously seen. Again, as previously noted, the derivative of this function f turns input velocities from Rn into output velocities in just R. So velocity in you only have a single output variable. That means literally just rate of change of whatever that scalar value is. Now, another thing that this smacks familiar of is, remember we've discussed previously that if you have a single row derivative matrix, then that is computationally equivalent in multiplication to dotting with the gradient vector. I mean, structurally, it's a little, technically this is a matrix, not a vector. This is a vector, not a matrix, right? But it's all the same elements, and you're doing the same this times that. Arithmetically, it's really exactly the same, right? So you have now the new option, because there's only one output, new option that you can, if you would like, for whatever reason, doesn't matter, but if you want, you can think of the derivative matrix as dot product with the gradient vector. So again, now this is not new. We discussed this back at the end of section 2.3. This is just, again, showing that old news is a special case of the chain rule. Right? Okay. All right, so here is yet another example. And again, I'm going to be real quick with this because it's morally equivalent. I could totally and maybe should view this as an example in 2.3. Okay. So input velocity, output velocity, and dot product with the gradient is the relationship. So here our function, our function gives temperature as a function of position. Notice that means there's, temperature, of course, is just a scalar. It's a single number. I have a real valued function here, and thus a single row derivative matrix, or if I might prefer, as I am doing in this example, just dot product with the gradient. Okay. And again, input velocity, you multiply by dot product with the gradient to get the output velocity. Colors, sorry. The output velocity that was requested. And, again, you got to take the appropriate partials, plug in the appropriate point. That's all arithmetic. But again, old idea. Again, this is section 2.3 stuff. How about that, though? It's a special case of the chain rule. Okay. Everybody okay? All right. Okay, so here's a different point of view on the chain rule. A lot of books start with this. I think there's a case to be made for that. I prefer to view this as a consequence of what we already know. Ultimately, I know that when students look at this argument here that we made about how you're composing functions and derivative matrices relate velocity vectors, I know there's heavier ideas going on here, but ultimately this is the natural way to think about things. These elements of these spaces, like this point right here, should not be thought of as two coordinates. It should be thought of as one point. That's what it is. It's a point, right? And coordinates they have their moments. Computationally, they're useful, I guess, right? But conceptually, what is this? It's not a couple of coordinates. This is a single point, right? So I think this is the more natural way to view things, and conceptually the most, this is what's going to stick with you the longest, right? So I like to start with that. But that said, here's a alternative take. Suppose I'm composing these two functions. Notice that what comes out of F is also what goes in to G, right? So this is literally a sequence. Concatenation of two functions about which we'll be interested in the composition. And here's the chain rule. Again, it's just a derivative of the product. Derivative of the composition is the product of the derivatives. Now, notice this matrix right here is all the various partials of the y's with respect to the x's, This matrix right here is all the various partials of the z's with respect to the y's. And the product is all of the various partials of the composition. The z's thought of as functions of the x's. Right? Everybody good? So all I'm doing, the only thing that's new about this is I'm writing this product of matrices with the elements kind of all, visible. That's all that I'm doing different. And now I'm going to ask a seemingly reasonable question, which is, okay, suppose that I'm only interested in one of these partial derivatives. And this, you'd be surprised, this actually comes up a lot, that I don't need to know how every one of the outputs is changing with respect to every one of the inputs. I just need to know this one partial. So, neat observation, that one partial, you can just write down how matrix multiplication works. Y'all remember this from long ago, but you use the equivalent row, right? And then you dot that with the corresponding column, right? And row dot column. That's how you multiply matrices. Is that good? So let's see here to kind of highlight it all to get. Oh, I should have left that. But anyway, these elements in the appropriate row get multiplied by the corresponding elements of the appropriate column, and altogether, this one element of the derivative matrix is known by this little simple formula right here. Okay. Now there's a bunch to say about this formula and how to interpret it. The very first thing I want to write, a lot of students will write down this equals this, and then they'll kind of stop and say, but wait a minute, I feel like I'm done here, because if I can get this to zoom in, because can't I cancel? This denominator looks just like that numerator, and boom, and then the result seems to be, at least as the notation lays on the page, right, that I've got the partial of zi with respect to xj. Kind of tempting, isn't it? It is very tempting. And this is 100% absolutely wrong. So you cannot do that. It does not make any sense. I blame the notation. The notation is at fault. If we look at, if I can get this to, there we go. If we look at that specifically, this term here, and look at the partial y1s that we canceled, and let's think about what roles they are playing. What is this thing, partial y1? This thing, by itself, doesn't mean anything. Because it depends on the context. It depends on, what's the story that this is one of the participants in? What's the function of what? And what am I holding constant? And what's allowed to be changing? And every one of those stories is different. In particular, this partial y1 represents a story where I'm looking at zi, and because I want the partial with respect to y1, I need all the other y variables to be constant, right? So for this one here, all the other y's are constant, because that's what partial derivatives mean, right? Well, in this expression here, we make no such assumption. In fact, quite the contrary. This is a totally different story over here when we write this partial derivative. Completely different scenario. In this scenario here, we're taking a partial with respect to xj, which means all the other x variables are constant, but then I'm going to be changing xj, which I claim means that as you change xj, all of the y variables will be changing. You're changing one of the inputs. that determines these other y variables. So these are completely different scenarios, and saying that this partial y1 here and this partial y1 here, saying that those are the same would be kind of analogous. I like analogies. Kind of analogous to saying, oh, well, I watched this movie one time. One of the characters was named Steve. But then 10 years ago, I watched this other movie, and it had a character named Steve, so I guess they're the same person. It doesn't make any sense, right? Yeah, same name. Okay, sure, they do have the same name. But they're part of different scenarios, different stories. They have nothing to do with each other. So you cannot cancel that. Everybody buy it? It's a dangerous little landmine because, again, you're going to get severely wrong answers if you are not comfortable with this point. So this is a wildly wrong statement because you need all of the other terms to make it a true statement. Okay, so don't step on that landmine, please. All right, let's see here if I can. Okay, there we go. So moving along, now here's a different take on this equation. Same exact equation, just recopied from the previous page. This is how I like to think about it in a lot of contexts, and in a lot of contexts, this is a real time saver. This mechanically, computationally, this is your friend, right? So here's a picture of the different variables. You know, we have the original x variables, and then there are the intermediate y variables, and then there are the eventual output z variables. Right? And every one of the variables to the right is a function of the variables to the left. Right? Let's consider a scenario where we're computing this partial derivative. Right? So we're taking the partial with respect to xj. So xj is allowed to change. But it's a partial derivative. And so that means that all of these variables, all the other x variables, are all constant. And let's just think it through, you know, looking on the diagram, what then actually happens with all these other x variables constant. If I jiggle xj a little bit, just allow xj to change just a bit, well, a bunch of things are going to happen if I do that, right? If I start fiddling with the value of xj, all these y variables are going to change. And each one of them, for example, let's take y1. Any change in y1 will make its own contribution to how much zi changes. Right? In other words, if you were to forget about the whole left function, you change y1, that's going to make zi change. But then also, if you change y2, that also will make zi change. Right? So there's this is what I like to call a propagation of changes, and the changes propagate along what I like to call paths. So let's see here, we'll use this color. As I change xj, that'll cause y1 to change, and as I change y1, that will contribute to zi changing. And notice those two factors are right there in this first term. So thinking about how changes propagate along paths allows you to kind of have a nice little motivation for the terms that we know from the chain rule are going to have to contribute to the formula that we're interested in. So as xj changes, I want to know how much zi changes. Well, this is one of the terms right there, what I call the y1 term in this formula. Everybody on board with that? Okay. Then also, let's look at the y2 term, or the y2 path, right? As xj changes, y2 changes, and then as that happens, then also zi changes. There's another term, the second term up here. That is what you would call the y2 term, and et cetera, and then lastly down here, as xj changes, that'll cause ym to change, which in turn will cause zi to change, and that gives you this, what I call the ym term. Does that all make sense? So what's beautiful about this is that allows you to kind of, I'm not encouraging this, but you could hypothetically kind of forget all about the matrix form of the chain rule, and just whichever partial derivative you need, if I can get this to, there we go, whichever partial derivative you need, you can just kind of write down the terms by just keeping track of all the different paths, each one of which, of course, is going to go by way of a different intermediate variable. So this is sometimes called the intermediate variable's point of view on the chain rule. All right. So can be very convenient in some circumstances. For example, let's look at this question right here. A couple functions given. I want to compute a partial of the composition. Notice that we are taking the partial of Z2, which is one of our eventual outputs, and we're taking its partial with respect to X2, which is one of our initial inputs. All right, so again, this is a partial derivative that goes through the composition. Okay. Step one is to draw yourself a little roadmap of variables. I'm a huge fan of this. I think it would be almost just asking for problems to not draw your little diagram. Notice this is just a kind of a adapted rip-off of this diagram, where the whole point to this diagram is that we can see the paths, and the paths tell me the terms that I need in my formula. Right? So please, 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 please make sure that in a question like this, where you'll notice no diagram is given, right? That should be your first thing to do. Draw your diagram. Notice that the first function, I should clarify, not the one that's written first, but the one that acts first, right? I represent like so. This is the relationship between the variables. You don't need to put these formulas in here. Just lets us recognize that y1 and y2 are functions of x1, x2, and x3. Okay, just represent that on the diagram. Then likewise, this is the function that acts second. Note that what comes out of f is what goes into g. And so, again, you write those down, get those variables straight. And now, let's see here. We were asked to compute the partial of Z2 with respect to X2. All right, well, Z2 is there. X2 is there. I don't have to think about derivative matrices. I don't have to compute a ton of partial derivatives that I'm going to end up not using anyway. I can just see exactly what the appropriate paths are here. And in particular, the first path goes through the intermediate variable y1, and so you get what I would like to call a y1 term in your chain rule. And then likewise, oh gosh, colors. Am I kind of out of colors here? Can I use yellow? Is yellow visible? Ooh. Well, maybe a little bit. There's your y2 path. Y2 is is the second intermediate variable, and then you get a y2 term in your chain rule. Right, so the diagram tells you, suitably interpreted, what your chain rule formula should be. Everybody on board? And it's all downhill. From here, it's just computing various partials. For example, let's compute the partial of Z2 with respect to Y1. All right, well, here's Z2. All right, there it is, Z2. It's y1 cubed. And what is the partial of this with respect to y1? Well, that's an easy partial derivative, and it's 3y1 squared. Et cetera, et cetera. and all together you combine it at the end, and the thing I was looking for is this expression. Everybody happy? All right. Okay. Let's talk about confusion of variables. This is a real problem. I'm going to start off by pointing out how ridiculous it would be to make a mistake like this in a single variable calculus class, because I know you all are all really good at single variable calculus, and I think it'll be clear and satisfying why this is silly in that context, and then we'll just apply the same ideas to the multivariable context. So, okay, here's a couple of functions. F of x is x squared. Nothing wrong with that. G of x is x cubed. There's nothing wrong with that, as these are two perfectly fine, reasonable functions. The question asks, what is the derivative of the composition? And now we have a problem. We might not have seen the problem yet, but I claim even by asking this question, we have a problem. So let me just proceed naively, and we'll see what happens. We'll see we get a wrong answer. We know the derivative of composition is the product of the derivatives, and let's see here. G prime, the derivative of G is 3x squared. That's easy. And let's see, F prime. Right, the derivative of x squared is 2x, and so it kind of seems that the derivative of the composition, being the product of the derivatives, should be 6x cubed. And yet we know that that's absolutely wrong. I mean, the composition is x to the 6th. The derivative should be 6x to the 5th, not 6x cubed. Right? Now, what's the mistake that I made? Well, I played fast and loose with my interpretation of how the chain rule works. Derivative of composition is the product of the derivatives. I just kind of wrote it down sloppily. I wasn't careful about what was being evaluated where. Here's what, if I wanted to be more careful, I suppose, I would have written down, right? It's not just G prime evaluated wherever, I don't know, wherever seems convenient, right? No, it's specifically evaluated at f of x, right? So the awkwardness of this is that your G prime being 3 times the square of wherever you're evaluating it, it is f of x, namely x squared, where you should be evaluating it. So it's not 3x squared, it's 3x squared squared. Right? So, I mean, it's annoying, but that's what you got to do, at least as we have things set up here. I point out, this is just an opinion now, but I think even this computation is, I think this is a bad idea. This relies on the student to remember that x is playing different roles in different parts of the question. That x, in this context, x has to be the thing that goes into f that gets plugged in into here, right? But as you're taking the derivative of g prime, x isn't the input to f. X is it's the thing that you are plugging into g prime. It's effectively f of x in this context. That's super confusing. And I claim that we have, in fact, literally committed a crime called confusion of variables. So look how easy it is to avoid this problem. All I have to do is just recognize that when I compose a function and another function, the thing that goes in to the second function has to be the thing that came out of the first function. Right? So the name that I give to G's input, well, it better not be X. G does not act on X. It acts on Y, whatever the output from, not the input to F, it acts on the output from F. So don't call this X. That's literally a confusion of variables. You're going to confuse yourself. You're going to screw this up. It's just going to happen. And so much easier to just, let's call this y instead. Let's realize that that means that I need to rewrite this function. I'm not going to change the function. I'm just going to write it now in terms of an appropriately chosen dummy variable, right? This is just a formula this is a fancy way of saying that g cubes stuff, right? And what I use as the placeholder in my algebraic notation for saying, hey, g cubes stuff, I'm just going to call it y instead of x. I could call it Steve. It doesn't matter, right? G takes whatever you put into it and it cubes it. Call that whatever you want. But don't confuse your variables, right? So, having rewritten it, notice how easy it is to deal with the actual question. Then I can be as sloppy as I want. I can write the derivative of the compositions, the product of the derivatives. Cool, fine, playing fast and loose. There are those two derivatives. Now, notice the g that I'm taking the derivative of is written in terms of y, so I get 3y squared. And then that serves to remind me that, let's see here, color choices again. That serves to remind me that what this y is, what am I going to do with that y right there? Well, that y needs to be the output value of f. So that's what's going to go there. And then you work out the algebra, and boom, correct answer is 6x to the 5th. So the nice moral of the story, if you just have a diagram showing your functions and your variables, and just make sure that you don't commit any crimes by confusing variables and having x be both an input and an output for the same function. You can't do that. That doesn't make any sense. At best, that's dangerous. Right? As long as you just don't do that, straightforward, no problem. The notation keeps track for you of what it is that you should plug in for what. All right, so that's all single variable calculus. You all know single variable calculus. But let's take this idea of confusion of variables and revisit the question when we're talking about a multivariable composition derivative. Right here, I'm composing two functions. Want to find now the derivative matrix. There's nothing wrong with writing f like this. There's nothing wrong with writing g like this until I decide that I want to compose them. And the very moment that you say you want to compose them, all of a sudden, as you compose them, and having chosen to write f in terms of the variables x and y, that means that I can't call these outputs x and y. It no longer makes any sense to have those be the inputs to g. I can't have them be x and y. They have to be the outputs from f, which can't be x and y. So let's just rename them. Right? All I'm going to do, because of this circumstance, is just rewrite g, no longer using x and y as my dummy variables. Now instead, just same exact function. I'm just going to use u and v as my dummy variables. Same exact function. It does not change g at all. I'm just writing it differently. And now, no confusion of variables. Write down the chain rule. Bada bing, bada boom, right? Don't even worry about where you're evaluating stuff. Your notation is keeping track for you of where you're evaluating stuff. And so, let's see here. So I have, we wanted the derivative of the composition. That's the product of the individual derivatives, which I can write down very conveniently. The derivative of f is there. The derivative of g. Oh, look what I did. Sorry. The derivative of f. See, it's really easy to get those backwards. See, I had them in the wrong order, didn't I? Watch out for that. So easy to mess that up. So there's the derivative of f. Here is the derivative of g. And everything's straight, and you just have to, plug in appropriately, and everything all works out. Now, one last little quick reminder, and then we'll call it a day. Do keep in mind that, once you get down to this form and the question comes up, wait a minute, what is this u right here? Well, recall that u, being the first input for g, is also the first output from f, which means u is x squared plus y squared. And likewise for v, second input for g, second output from f is x squared minus y squared. Okay, all right, this is a good stopping point. See y'all later. Have a good one. Don't forget, test on Friday. Good luck with your studying. See you then.